For this tutorial, we've prepared 3 virtual machines using VirtualBox, running Debian-based operating systems. Let's go through our specific configuration. Our machines ELK Test 1, ELK Test 2, and ELK Test 3 have been allocated different resources based on their roles. For the hot and cold data nodes, we've assigned 8 GB of RAM each, while our frozen data node receives 6 GB. Storage-wise, we've provisioned 40 GB for 2 machines and 50 GB for the third. To ensure optimal performance, we've configured 4 CPUs for the hot and cold nodes, while the frozen node operates with 3 CPUs. SSH server configuration. To optimize our resource usage, we'll be running these VMs in headless mode and managing them through SSH connections. This eliminates the overhead of graphical user interface rendering on our host machine. We'll need to install OpenSSH server on both our VMs and our WSL environment to enable this functionality. System preparation. Let's begin by accessing root privileges using the su command. We'll then run a series of commands to set up our SSH server. apt get update, apt-get install OpenSSH server, systemctl start SSH, systemctl enable SSH. After executing these commands, we need to modify our VM network settings. Navigate to the network section and change from NAT to bridged adapter. This change is crucial for enabling proper network connectivity. We'll then reboot the machines to apply these changes. To verify our network configuration, we'll use the ipadr show command to obtain our IP addresses. Establishing connectivity. With our IP addresses in hand, we can now establish SSH connections. We'll use the command syntax SSH username at IP address to connect to each machine. You'll need to authenticate using the password we configured during the initial VM setup. Once connected, we'll switch to the root user to ensure we have the necessary permissions for our upcoming configurations. Elasticsearch installation process. After organizing our terminal windows for efficient management, we'll proceed with the Elasticsearch installation. First, we need to install curl using apt-install curl. This tool is essential for securely downloading and verifying our Elasticsearch GPG keys. Package configuration. In this part of the setup, we're configuring the system to install Elasticsearch directly from Elastic's official repository, ensuring we're using secure and verified packages. First, we're adding a GPG key from Elastic's repository. Next, we're adding the Elasticsearch repository to our system's list of sources. This repository is where the latest Elasticsearch packages are maintained. After adding the repository, we run an update to refresh the list of available packages, including the newly added Elasticsearch options. Finally, we install Elasticsearch. This process sets up the main components and dependencies required to run Elasticsearch on this system. Once installation finishes, the system will generate an initial password for the default Elastic user. This password is essential for the initial setup, so make sure to save it securely. Although you'll be able to change it later, having access to this initial password is crucial as we configure Elasticsearch further. Next, we'll configure the first Elasticsearch node to set up our cluster. First, we'll start Elasticsearch on this machine by running a command to initialize the service. With Elasticsearch running, we can now move on to editing the main configuration file, known as elasticsearch.yml, where we'll adjust settings specific to our cluster setup. We'll set a unique cluster name, which is like an identifier for our cluster. Next, we define the node name, which will identify this specific machine within the cluster. We'll also specify the role of this node. By assigning it the roles of master and data hot, we're setting it up to manage critical cluster functions and handle data storage tasks according to our project's needs. We'll adjust the network settings so that the cluster is accessible over the network by setting the host to 0.0.0.0 and configuring the port to 9200, the standard port for Elasticsearch. We're leaving other settings, like the security configurations and data and log paths, at their default values, as they're already optimized for this setup. These changes form the foundation of our cluster and prepare this first node to interact with additional nodes that we'll configure in the following steps. Verifying node configuration. To ensure our first node is set up correctly, we'll run a couple of commands to test the connection. We'll start with a quick command to check that Elasticsearch is up and responding. This command bypasses certificate verification and uses the Elastic username along with the auto-generated password from the security configuration stage. This will give us a response showing essential details about our Elasticsearch instance, like the node name, cluster name, unique cluster identifier, version info. For a more secure connection test, we'll use a command that references a specific certificate file. You'll still enter the Elastic user's password when prompted, but this method helps keep your password hidden in your terminal history. Next, we'll set a new password for the Elastic user to improve security. For this, we navigate to the directory where Elasticsearch binaries are stored and use a reset password tool. This utility allows us to choose a new password in a secure, guided process. Let's verify our configuration through a web browser. Open your browser and enter the following URL. Start with HTTPS, followed by your virtual machine's IP address, then add port 9200. Since we're accessing this from our host machine's browser, remember to use your virtual machine's IP address. Enter the username Elastic along with your newly set password. You should now see the same cluster information we previously viewed using curl. Review our configuration file. It's named elasticsearch.yml and is located in the etc Elasticsearch directory. Third, restart the service by typing systemctl restart Elasticsearch. Let's check our cluster's health. In your browser, enter HTTPS, your virtual machine's IP address, port 9200, followed by _cluster/health. At this point, you'll only see our initial node listed, as we haven't added the other nodes yet. We need to generate enrollment tokens from our first node, ELK test 1. Navigate to the USR share Elasticsearch bin directory and enter this command, Elasticsearch create enrollment token -s node. We'll need to run this command twice, once for each node we'll be adding. Make sure to save these enrollment tokens carefully. They contain crucial information for expanding our cluster. Second node configuration. We'll move to our second virtual machine and begin the node configuration process. First, navigate to the Elasticsearch binary directory. Second, use the enrollment token from our first node to reconfigure this node. Enter the command Elasticsearch reconfigure node, followed by 2 dashes and the word enrollment token, then paste your enrollment token. Third, when prompted, confirm the reconfiguration. Now, we'll modify the elasticsearch.yml file for our second node. We need to uncomment and modify specific lines to configure this node as our cold data node. Here are the settings to change. Set cluster.name to match our existing cluster. Set node.name as ELK-test2. Set node.roles as data_cold for our tiered architecture. Configure network settings. Set network.host to 0.0.0.0 and http.port to 9200. Keep the default paths for data and logs. Finally, start the Elasticsearch service on ELK-test2 by typing systemctl start Elasticsearch. Let's enroll our third node. First, generate a new enrollment token from our first virtual machine. Run Elasticsearch create enrollment token-s node. Switch to your third virtual machine's terminal. Navigate to the Elasticsearch directory and enter Elasticsearch reconfigure node, followed by 2 dashes and the word enrollment token. Then paste your new enrollment token. Let's verify our cluster's health. Open your browser and refresh the cluster health page. If our second node has joined successfully, you'll see the number of nodes has increased to 2. For a more detailed view, check the nodes API by entering HTTPS, your virtual machine's IP address, port 9200, followed by _nodes. This gives us comprehensive information about our cluster setup. To analyze this data more easily, copy the JSON output and paste it into jasonpathfinder.com. This tool will help us examine important details like host names, node names, and role configurations. Third node configuration. Let's continue configuring our third node. When prompted to continue the reconfiguration process, type Y and press Enter. Next, we'll edit the elasticsearch.yml file using the Nano text editor. We need to modify and uncomment several crucial settings. The key configurations include: set our cluster name to ELK test cluster, define the node name as ELK-test3, assign the role of data_frozen, configure network settings to allow external connections. Troubleshooting and cache configuration. If you encounter an error when starting the Elasticsearch service, don't worry, this is expected. For frozen nodes, we need to specify a cache size. Add the following line to your YML file: xpack.searchable.snapshot.shared_cache.size, followed by 30%. After saving these changes and restarting Elasticsearch, the service should start without errors. Cluster verification. Let's confirm our setup. Refresh the cluster health page once more. You should now see 3 nodes listed in the cluster. The nodes API will show detailed information about all 3 nodes, including their names, IP addresses, and assigned roles. In Installing additional components. We'll enhance our setup by installing Kibana on our first virtual machine and Logstash on both our second and third VMs. Here are the commands we'll use. For Kibana on VM1, type apt install kibana-y. For Logstash installation on virtual machines 2 and 3, enter apt install logstash-y. Note that installation times vary. Kibana needs about 340 megabytes, and Logstash needs about 430 megabytes. File access setup. To give Logstash access to Elasticsearch logs, add the Logstash user to the Elasticsearch group on your second virtual machine with sudo usermod-ag Elasticsearch Logstash. This lets Logstash read and process the Elasticsearch logs. Now let's set up the Logstash pipeline. Create a configuration file using nano. Customize the cluster name for your setup using nano followed by etc/logstash/conf.d/, then your cluster name, followed by -logs.conf. The configuration needs two main parts. The input setup will watch JSON log files in the Elasticsearch log directory, read from file beginnings, use JSON for parsing. The output setup will connect to all 3 Elasticsearch nodes using HTTPS, create daily indices with the pattern ELK test cluster logs-date, set up authentication and SSL certification. On the first virtual machine with Kibana, set up secure access. Reset the Kibana system user password with Kibana. Kibana's configuration file with nano etc/kibana/kibana.yml. Change these settings. Port to 5601. Allow connections from any IP set. Elasticsearch hosts. Configure authentication. Disable SSL verification for the demo. Troubleshooting. You might see issues during Kibana's first setup. It needs a data content node for default indices, which our cluster doesn't have yet. If you get a Kibana login error and see a red cluster status, check these things. Check shard allocation in your browser. With HTTPS, your VM's IP _cat/shards. For allocation details, check HTTPS your VM's IP _cluster/allocation/explain ? The error will show that shards can't be allocated because we need nodes with the data content role. You might see issues during Kibana's first setup. It needs a data content node for default indices, which our cluster doesn't have yet. Let's fix this by modifying our first node's configuration. Go back to your first virtual machine's terminal and edit the elasticsearch.yml file to add the data content role. After saving your changes, we'll need to restart both services. Enter these commands: systemctl restart Elasticsearch. Then, systemctl restart Kibana. To verify our fix, refresh the _cat/shards page. You should now see all shards in the started state. The allocation explain page should show there are no unassigned shards in this cluster, indicating we've successfully fixed the issue. Now we access the Kibana and set up ILM policy can access Kibana through your web browser. Log in using the Elastic user and your chosen password. Follow these steps. Click Explore on my own from the Welcome page. Navigate to the Management section in the left pane. Select Index Management under the Data section. Now let's set up our index lifecycle management policy to handle data retention across our tiered architecture. Open the console tool and we'll create a comprehensive ILM policy that will handle hot data for the first 10 days with a 40 GB size limit. Move data to the cold tier after 10 days, optimizing storage with force merge. Transfer data to the frozen tier after 20 days for long-term retention. After executing this policy configuration, you'll see a 200 OK response with acknowledged true, confirming successful creation. You can review and modify this policy anytime through the Index Lifecycle Policies section in the left navigation pane. In the next step, we'll be creating index template to define how our indices should be structured. Open the Management console. Let's create this template using the PUT command in the console. This template configuration matches indices following our cluster's naming pattern, sets up one shard and one replica for each index, associates our previously created lifecycle policy, establishes a rollover alias for seamless index transitions. Let's continue by returning to our virtual machines to configure the Logstash pipeline. First, we'll reconnect to our third virtual machine using SSH. Once connected, we'll switch to the root user by typing SU, followed by Enter. Moving on to our second virtual machine, we need to modify the Logstash pipeline configuration. We'll focus on changing the index naming pattern in the output section. Currently, we have a static index name that looks like your cluster name, followed by -logs. We're going to make this more dynamic by adding date information. The new pattern will be your cluster name, followed by -logs-, and then the date in year, month, and day format. This change is important because it allows our system to automatically create new indices based on the dates in our log files, which helps with data management. On our second virtual machine, let's start the Logstash service. Type systemctl start Logstash and press Enter. To check if it's running properly, enter systemctl status Logstash. To verify the index creation, open your web browser and navigate to the Kibana interface. Go to the Index Management section. You should see a new index that contains about 175 documents. Look at the lifecycle section of this index. It will show you which phase it's currently in and how it's progressing through our lifecycle stages. Remember, this index will move to the cold phase when it either reaches 40 GB or becomes more than 10 days old. Now we need to configure Logstash on the third VM. Let's move to our third virtual machine. First, check Logstash's current status by typing systemctl status Logstash. Now we'll copy the configuration from our second virtual machine. On the second VM, view the configuration by typing cat, followed by etc/logstash/conf.d/ and then your cluster name followed by -logs.conf. Take this configuration and create the same file on the third virtual machine. Once you've copied it over, start Logstash by typing systemctl start Logstash. Now let's set up our data views in Kibana. 1. Go back to Kibana and refresh the index management page. 2. Create a new data view for our indices. 3. Configure the index pattern to match how we're naming our log files. 4. To handle any pattern matching issues, we'll create an empty index that matches our pattern. Set up an alias to combine our indices. Configure the data view with the correct pattern name. This setup will help us analyze data across all our indices while maintaining proper lifecycle management. Exploring index documents. Let's look at the documents in our index. Go to the Discover view in Kibana. You'll find several fields in our log documents, including timestamps, version information, error messages and their types, log levels, host names. Before verifying our pipeline, give the pipeline some time to process the logs. You'll notice the number of documents increasing as logs from both our second and third nodes are processed. All this data is being stored in the hot tier on our first node, which we're accessing through Kibana. Let's check if Logstash is installed on our first virtual machine by typing systemctl status Logstash. Since it's not installed, we'll install it by typing apt install Logstash, followed by -y. After installation, we need to 1. Add Logstash to the Elasticsearch group by typing sudo usermod-ag Elasticsearch Logstash. 2. Create a pipeline configuration file that matches our other nodes. Three, start the Logstash service. Learn verifying data ingestion. First, let's verify our data pipeline is working correctly. Open your web browser and navigate to the Kibana interface. Go to the index management section and refresh the page several times. You should notice the document count increasing. Click through to the Discover view of your index. You'll notice many new fields have appeared in our data. Since these are different JSON files, they contribute various unique fields to our index. Look at the left sidebar and find the Analytics section. Click on Dashboards. We're going to build this dashboard completely from scratch, so click Create Visualization. Before we begin, double-check that you're using the correct data view. It should be the one we created earlier. Let's create several visualizations to help us understand our data. Marsh Records metric. Let's start with a simple metric. 1. Look for the records field in the available fields list. 2. Drag it to the center of your workspace. This will be our foundation. 3. From the visualization types, select Legacy metric. Click Save and return to your dashboard. Timestamp distribution. Now let's visualize our data over time. 1. Create a new visualization. 2. Find and drag the timestamp field to your workspace. 3. Choose the bar horizontal stacked visualization type. 4. Add a breakdown by virtual machine name. This will show different colors for each VM. 5. Adjust the timeframes to match your analysis needs. 6. Save this visualization and return to the dashboard. Trace ID analysis for tracking our operations. 1. Create another visualization. 2. Find and drag the trace.id.keyword field to the center. 3. Select the donut visualization type. Important, look for the advanced section in the right panel. 5. Find and disable the option that says Group Remaining Values as Other. This default setting can make our data harder to understand. 6. Save and return to the dashboard. Log file path distribution. To understand where our logs originate. 1. Create a new visualization. 2. Locate and drag the log.file.path.keyword field into your workspace. 3. Keep the default bar vertical stacked style. It works well for this data. 4. Save and return to the dashboard. Logger information. For a detailed view of our logging sources, 1. Create another visualization. 2. Select the log.logger.keyword field. 3. Choose the donut visualization type. 4. Again, disable Group Remaining Values as Other in the advanced settings. The default setting can obscure important details. 5. Save and return to the dashboard. Log level distribution. Let's analyze our log severity levels. 1. Create a new visualization. 2. Drag the log.level.keyword field to the workspace. 3. Select the pie chart style. 4. This visualization will reveal that the majority of our logs are info-level messages. Approximately 7.5% are warning messages. A small fraction, about 0.3%, are error messages. 5. Save and return to the dashboard. Thread analysis. Finally, let's examine our process threads. 1. Create your last visualization. 2. Use the process.thread.name.keyword field. 3. Choose the table visualization type. 5. Modify the settings to display only the top 6 values. 5. Save and return to the dashboard. Finalizing the dashboard. Make sure to save your entire dashboard to preserve all your work. One of the most powerful features of this custom dashboard is its interactive drilling capabilities. You can click on any element in any visualization to dive deeper into that specific aspect of your data. For example, clicking on a specific log level in the pie chart will filter all other visualizations to show only data from that log level. This interactivity makes it easy to analyze patterns and investigate any anomalies in your cluster's behavior. And that's it. You've now set up a complete ELK stack for comprehensive log management and analysis. This powerful system will help you centralize your logs, gain valuable insights, and monitor your infrastructure more effectively. I hope you found this tutorial helpful and informative. Remember, The key to getting the most out of the Elastic Stack is continuous learning and experimentation. If you enjoyed this video, be sure to subscribe to my channel for more tech tutorials and projects. You can also follow me on Medium, GitHub, and LinkedIn to stay up to date with my latest content and connect with me. Thank you all for watching, and I'll see you in the next one. Take care.